I'm Hassan Najafi, the session chair of session 4A, Stochastic and Approximate Computing. In this session, we will have 4 paper presentations. The pre-recorded video of each presentation will be first played. After each presentation, we will have a few minutes for questions from the speaker. Attendees can either ask and write their questions in the chat box or directly ask the questions at the end of presentation from the speaker. So let's begin by the first presentation. The first presentation will be for paper 2 input, 4 output programmable spin wave logic presented by Abdulqadir Mahmoud. Let's begin. Let me share my screen.
Hello everyone, my name is Abdulqadir Mahmoud and today I'll present to you my paper which is about 4-output spin-wave programmable logic gate. I will give a brief introduction about spin-wave based technology in the introduction, then I will move to the proposed structures of the programmable logic gate. After that I will discuss the simulation results and performance comparison, and in the conclusion I will sum up. The information technology revolution caused rapid increase of the amount of raw data together with the requirements of efficient computing platform for their processing. CMOS downscaling has been efficient to meet these requirements. However, CMOS downscaling become very difficult due to leakage wall, reliability wall, and cost wall, which implies that Moore's law will come to the end soon. Hence, different technologies have been explored recently. One of them is spin-wave based technology. Spin-wave based technology stands apart as a promising alternative avenue because its wavelength can reach down to nanometer, its frequency can reach up to terahertz, it has an ultra-low power consumption, and it has acceptable delay and intrinsic data parallelism. The proposed 4-output spin-wave programmable logic gate, as you can see here, C1, C2, I1, and I2 are the inputs of the structure, while O1, O2, O3, and O4 are the outputs of the structure. In order for this structure to function correctly, D3 to D8 must be the multiple integer of lambda such that when the spin waves are interfering and if they have the same phase, then they will interfere constructively and they will interfere destructively otherwise. In addition, this gate can provide the inverted and the non-inverted output by choosing D1, D2, D9, D10 differently. If the non-inverted output is desired, then the distances must be multiple integer of lambda, whereas n plus half multiplied by lambda must be the distances if the inverted output is desired. In addition, there are 2 ways to detect the outputs. Detection based on the phase, such that if the detected spin wave is has a phase of 0, then the output is logic 0, whereas if the detected spin wave has a phase of pi, then the output is logic 1. On the other hand, if the detection based on the threshold is the used mechanism, then the detected magnetization of the spin wave will be compared with a predefined threshold, such that if the detected spin wave magnetization has value greater than the threshold, then the output is logic 1, whereas it is logic 0 otherwise. As you can see here, C1 and C2 are closer to O3 and O4 than O1 and O2, which cause unbalanced gate. In order to balance the outputs, we moved C1, C2 to the middle in order to make O1, O2, O3, and O4 have the same energy and achieve the fan-out of 4. In order to validate this gate, we made use of these parameters and we fed them to the micromagnetic software, which is object-oriented micromagnetic framework. Here are the validation of the unbalanced programmable logic gate and programmable logic gate. In the figures, blue presents logic of 0 and red presents logic of 1. Here, once the left as the control is 0, then it represents AND of the 2 inputs, whereas in the right, as it is the control is 1, then the outputs O2 and O4 are the OR of the 2 inputs. And you can analyze, as you can see here, 0, 0, 0, 1, 1, 0, 1, 1, 1, which represent AND OR of the inputs. The same holds true for the balance. As you can see here, this one are the magnetization output of the unbalanced one, and this one is the magnetization of the balanced one. In order to construct XOR gate, we need to define a threshold which is 0.35. It's the average between these two values, such that if the magnetization is greater than 0.35, which is 0.9 and 0.3, then it is 0, whereas if they are less, then it is 1, then it is 0, 1, 1, 0, which is XOR gate. The same hold true for the balanced gate. However, as you can notice, O3 and O4 as the unbalanced distribution of the outputs, we cannot construct XOR and XNOR. However, in the balanced one, we can construct in O1, O2, O3, and O4 the XOR gates based on a new threshold, which is 0.38, which is the average between 0.43 and 0.33. Moving to the performance comparison, as you can see, our evaluation indicates that while 11 times slower than the CMOS counterpart, the proposed gate provides a 16 times less energy consumption reduction. Whereas when comparing with the state-of-the-art spin-wave majority gate, the proposed structure saves 3 times energy while keeping the same. In conclusion, we introduced and evaluated by means of ohm simulations a novel two-input balanced and unbalanced 4-output spin-wave programmable logic gate. We evaluated and compared with the state-of-the-art equivalent implementations in terms of energy consumption and delay. Our estimations indicated that the proposed gate provides 3 times energy reduction when compared with the spin-wave counterpart and 16 times energy reduction when compared to a 15 nanometer CMOS implementation, while it is 11 times slower than the programmable logic gate in the 15 nanometer CMOS implementation. Thank you.
Okay, thank you, Abdulqadir, for the presentation. We have Abdulqadir here, right?
Yes.
Okay. Yeah. Just a sec. Okay. Any questions from the audience? Okay. If not, let me ask a couple of questions. Abdulqadir, why didn't you validate your design using HSpice? Using a SPICE on a SPICE level simulation?
Thank you for your question. As you know, the SPICE, firstly, there isn't a SPICE model for spin-wave based technology because it is in its early stage development. As you know, to develop a SPICE model, we need accurate data for efficient spin-wave device, which is not available until now. Because of that, we did that in the micromagnetic simulation, which we hope by the end of this project to be able to fabricate an efficient device, which we can build a SPICE model from it. And then in the future, the researchers can use it to develop more gates and the circuit using spin-wave based technology.
All right. And what are the possible applications for the spin-wave technology?
Actually, thank you for your question. There are many applications for it. Since spin-wave is ultra low energy efficient technology, there are many applications. Example of them are we can develop spin-wave sensors. We can use them in microwave signal processing. We can use them in quantum magnetics. We can use them in terahertz applications since the spin wave enables the calculation in that frequency regime and in the holographic memory. I would like to forward the audience, if they are interested in this, to our paper, which discuss the fundamentals and basics of a spin wave based technology from physics and engineering point of view, which will be available soon in the Journal of Applied Physics, entitled Introduction to Spin Wave Computing. And it's available already in archive, so feel free to read it. And if you have any question, you can contact me directly.
Thank you, Abdulqadir. Let's go to next presentation. bespoke approximate behavioral processors presented by Rohit Sri Kumar. Do we have Rohit here or the speaker?
I'm Benjamin. I'm here. Yeah. Can you hear me?
Oh, yes. Okay. So we have Benjamin. Okay. Good. Let's first have the presentation and then we will go for questions. Let me share my screen.
Behavioral processors. My name is Benjamin Karian Schaefer, and I'm an assistant professor at the Department of Electrical and Computer Engineering at the University of Texas at Dallas. This work was done in collaboration with my graduate students, Rohit Sri Kumar and Prada Chaudhary. Let's look at the motivation of this work. Many emerging applications, like IoT and medical, require simple controllers that continuously execute this same application. These controllers need to be inexpensive, which implies that they have to be small as possible, and ultra low power. Now, not all the resources in a general purpose processor are always used. That means there's a large potential for simplification. For example, we can remove unused instructions. Now, at the same time, raising the level of processor design abstraction from the RT level to the behavior level has some key benefits. First, it opens the window to new optimizations, and second, it allows to fully re-optimize the processor design as opposed to pruning the logic at an already synthesized gate net list. Let's look at how we can design processors at the behavior level, means in C for high-level synthesis. If you look into this figure, the processor is completely defined in C, C++ system C. And it has two arrays, an instruction memory and a data memory array. The processor itself is basically a big switch case that has all the instructions, the processor. The processor is then synthesized using high-level synthesis into RTL, varilocal VHDL, and after logic synthesis, we obtain the gate net list. This is the hardware flow. Now, the software flow, the input is again C, but this is the application, the workload running on the processor. We use a cross compiler to create the machine code, right? And you see here you have the instruction memory that is stored into the array that the processor will then read, and the data memory. Let's look at the proposed flow. It's composed of four main phases. The first phase does some pruning of the instructions and basically deals with the software optimization, while phase 2, 3, and 4 deal with the actual pruning of the processor at the different level of VLSI design abstraction from the behavioral RTL to C. The input to the flow is the workload that will run on the processor in C, and the behavioral description of the processor. In this case, it's a scalar MIPS processor. Let's quickly review the different stages. Phase 1 deals with the reduction of the number of instructions. This is important because the less instructions our processor executes, the smaller the instruction memory becomes. And also, what we try to accomplish here is to reduce the different types of instruction being executed. Because as you can imagine, the type of instructions will affect the amount of pruning that we can achieve. And for that, this stage tries different compiler optimizations. Phase 2 does the pruning at the behavior level. So the input is the behavior description of the C processor, the MIPS processor. We profile, simulate the code, and we remove all the instructions not being executed. After this, we call the high-level synthesis tool, and our process generates synthesizable RTL code. And the advantage of this flow is that the high-level synthesis tool will fully re-optimize the RTL code based on the logic on the descriptions pruned. Phase 2 does the exact same thing at the RT level. After high-level synthesis, many more operations are made visible. Think about a for loop that has been unrolled, right? So now these operations within those for loops can now be pruned. So we do the same thing, profile, simulate, prune. And after this, we generate new RTL that is then synthesized to obtain a gate net list. The last phase does the same thing at the gate net list, right? We simulate, we profile, we prune the net list, and when we remove the logic that is not being used in the simulation, and obviously we need to do some stitching together to make sure that the functionality is still correct of the gate net list. The result of the flow is the gate net list of our bespoke processor. Let's look at the experimental setup. As high-level synthesis tool, we use NEC Cyber Workbench version 6.1. The logic synthesis tool is Design Compiler from Synopsys, the RTL Simulator Mentor from ModelSim, the scalar processor used, in our case, the MIPS processors taken from the CH-Stone benchmarks, and you see here the table, different workloads that we run on the processor. One important observation is the instruction utilization. Intuitively, the less instructions a workload uses, the larger the optimization of the processor, because more instructions can be pruned away. In the paper, we actually did a more detailed analysis, creating some synthetic benchmarks and showing how the instruction utilization affects the optimization of the processor. Let's look at the experimental results. And this figure shows the area reduction, power and delay reduction of our method compared to the state-of-the-art that does everything at the gate net list, the synthesized version of the processor. And we show that on average, our approach can lead to processors that are 71% smaller, consume 62.1% less power, and are 46.5% faster compared to the original general purpose processor. And compared against the state-of-the-art, we are about 9.3, 11.6, and 8.9% better in terms of area, power, and delay. Let's conclude the work. In this paper, we presented a method to simplify simple behavioral processors. We've shown that starting at the behavior level allows the processor to be re-optimized after each of the different VLSI design stages, leading to these extra benefits, right, in experimental results compared to just optimizing a processor. A general purpose processor specified in the gate net list version shows that we can achieve around 10% better area, small area, delay, and power. This concludes this presentation. Thank you for watching, and if you have any questions, please send me an email or write your comments in the chat. Thank you.
Okay. Thank you, Benjamin, for the presentation. Sorry for misintroduction. Rohit was selected as the presenter of this paper. That was the reason I introduced him as the presenter. So, any question from Benjamin on this paper? Okay, just a couple of questions for you. First, in the conference program, I see bespoke approximate behavioral processors for the title of your paper, but in the presentation, I didn't see the approximate word. Is this bespoke approximate or bespoke behavioral processors?
Yeah, no, the paper was a long 8-page paper, but as you've seen, it was accepted as a short paper. So we had to reduce portion of it, and it seems that the reviewer didn't like the approximate portion. So we went one step further to actually be allowed to introduce some error at the output, making even the processor simpler, but the reviewers did not like that portion. I guess that's why it was accepted as a short paper. So we cut that portion off.
Okay. And how does the complexity reduction of the processor get affected with the types of instructions used?
What do you mean with the complexity? So the processor basically gets simplified, as you see from the results, by almost 60 to 70%, because most of the applications, the fixed workload, do not use a large portion of the instructions. So those instructions, the logic of all these instructions can be completely pruned away. As again, this is for very simple controller circuits, those controller processors. So we simplify almost 60 to 70% of the process instruction.
Okay, got it. Okay, thank you, Benjamin, for the presentation and for responding to the question. And we can continue with the next paper, hardware-based fast real-time image classification with stochastic computing, presented by Ponana, Kaditira, Mortapa. Okay, let me share the screen and start the next presentation.
Hello everyone, and welcome to the short presentation on hardware-based fast real-time image classification with stochastic computing. The goal: to use stochastic computing to realize medium complexity convolution neural networks targeting real-time applications. Nowadays, various IoT devices generate huge amount of data at the source and are dependent on edge and cloud computing to process their data. Stochastic computing can be used for near-sensor computing, where data can be processed locally. It can also overcome the dependency on edge and cloud computing for medium-sized real-time applications. Also, the associated problems like privacy and security, latency and speed can be overcome, and thereby improving the overall performance of the application. Stochastic computing. It's a non-conventional low-cost approach where numbers are treated as digitized probabilities. Such numbers are called as stochastic numbers. For example, the binary number 0.75 can be represented as shown here. Both the representations has 75% ones and 25% zeros. The bit stream length is 8 bits wide. Circuits that process such numbers are called as stochastic circuits, and they have advantages like low complexity, power efficient, inherent error tolerance. For example, a single bit flip from 1 to 0 in the above number 0.75 would be a number 0.625, which is still the representable closest of 0.75. Also to note here, the position of ones within the bit stream is independent of the bit position because each bit position has the same weight. Here are the example of stochastic circuits. For example, AND gate is used as a stochastic multiplier to multiply two stochastic numbers. And also we have the two input mux, which is acting as a scale stochastic adder. The choice of convolution neural network is the popular LeNet-5 neural network. The architecture is shown here. It has two convolution layers with 6 feature extractors in the first layer and 16 feature extractors in the second layer. In addition, it also has 3 fully connected layers with 120 neurons in layer 1, 84 neurons in layer 2, 10 neurons in layer 3, which is also the output layer, which represents the possible 10 class outputs. In addition, each of the convolution layer is also followed by a max pooling operation. The input layer holds the input images, which are handwritten numbers from the MNIST dataset. The images are passed through convolution layer, followed by max pooling, and then the second convolution layer, and followed by another max pooling. The output of the second max pooling is flattened and is then fed to the fully connected layer. The number of trainable parameters and the number of connections that exist in each layer is shown at the top. The neural network is first built using C++ and is then trained using the MNIST training dataset and is then tested against the MNIST test dataset. The trained parameters are then extracted and is used to realize or construct the stochastic version of the convolution neural network. Stochastic convolution neural network building blocks. These building blocks are the components that are used to construct each layer within the stochastic convolution neural network. They are listed in the order of data propagation within each layer. Stochastic number generator. This is the source of stochastic numbers within the stochastic convolution neural network. All the trained parameters and the input pixel, which are in binary, are converted to their equivalent stochastic numbers. It is constructed using a random number source, which is a linear feedback shift register, and a 4-bit lookup table, which is also called as SBOX. The advantages of using this number generator over the other available ones is that it has reduced correlation between multiple stochastic numbers generated from the same random number source. Next component is the stochastic computing neuron. The schematic is shown here. It consists of a set of AND stochastic multipliers to obtain the products between the input pixel and train weights. Then we have the router logic that is used to route the negative products to the negative parallel ladder and positive products to the positive parallel ladder. The binary sum out of the parallel ladders is fed as an input to the FSM-based stochastic sigmoid activation function. Here is a plot of binary versus stochastic sigmoid activation function. The blue line represents the binary version while the orange represents the stochastic version. The output of stochastic neurons is fed as inputs to the stochastic max pooling unit. It accepts 4 stochastic numbers from 4 stochastic computing neurons. This is because the size of max pooling window is 2 cross 2. The advantage of using this max pooling unit over the others is that it can output the exact maximum of the 4 input stochastic numbers. The choice of stochastic number precision is 9 bits. This means all the train weights and the input pixels are all represented as 512 bits. Realization of stochastic convolution neural network. The choice of FPGA is the Xilinx XE7Z020. It offers a heterogeneous computing platform consisting of programming logic fabric and processing system, which is ARM Cortex-A9 CPU. The complete stochastic convolution neural network is realized on the programming logic fabric, which is shown in the red box here. It consists of an input layer, which is used to hold the input test images from the MNIST dataset. It also orders the correct pixels required for convolutional operation and also generate their equivalent stochastic numbers. Next, we have the first convolution layer, second convolution layer, and the 3 fully connected layers. Each of these layers mainly perform stochastic number generation, convolution, accumulation, activation function, and subsampling. The last layer performs classification operation. Each of these layers has got their own stochastic number generators. These generators are used to generate the stochastic numbers for the train parameters and the input pixel. Also, each of these layers has got their own instances of stochastic computing neurons, which perform multiplication, routing, parallel addition, activation function, and max pooling operation. The processing system, or the ARM Cortex-A9 CPU, executes a bare metal application. This bare metal application has got 3 main tasks. Initializes UART, GPIO, SD card interface. It then loads all the trained binary parameters, the 10K test images from the MNIST dataset and their labels from the SD card onto onboard DDR3 memory. At last, it performs evaluation of SCNN results against the test labels and then reports the classification summary via UART. Design decisions. The stochastic convolution neural network is designed for resource-restricted FPGA with resources as shown. Certain components within each layer is designed to be modular in nature and are subject to time multiplexed operation within the layer to complete the operations of that layer. For example, there exists only one hardware instance of SC neuron in the first fully connected layer and is used 120 times to finish the operation of that layer. Storage of intermediate stochastic results between the layers is achieved by using block RAMs and the associated control logic around it. Results. Classification accuracy. Now we have 2 models of the same Leonard neural network. One is the stochastic version and the other is the software version. Both of these models were subject to 10,000 MNIST and Fashion MNIST test images. It is evident from the results that the stochastic convolution neural network almost performs identical to the software version in terms of classification accuracy. Results. Power estimation. The FPGA development board has got only one current sense jumper pin to measure the overall power consumption of the board. There is no facility to make individual power measurements for each of the components present on the board. Hence, a separate power measurement for the FPGA alone was not possible. However, a sequence of power measurements was made during the operation of the board to get a more realistic power estimation of the stochastic convolution neural network. Power measurement was made when the board was powered on, programming logic configured with stochastic convolution neural network, and the processing system is running. Stochastic convolution is running and doing the classification task, stochastic convolution neural network finished the operation. From the table, it is clear that the power estimation when the stochastic convolution neural network is running and not running is approximately 96 milliwatts. Conclusions. A fully working and self-contained stochastic convolution neural network is developed, which can do real-time classification of handwritten numbers. The complete stochastic convolution neural network is realized just by using 52% of the available lookup tables and 25% of the available flip-flops in the FPGA. From the results, it is evident that stochastic computation can do accurate real-time image classification with small, low complexity and low power circuits. The previously explained stochastic convolution neural network building blocks can be arranged in a large variety of different configurations and thereby enabling many areas pre-designed trade-offs. References. Thank you for listening.
Okay, thank you for the presentation, Ponano. Any questions from the audience? I have a quick question. How is your work compared to related works in this area, especially considering the fact that there are some prior works implementing stochastic neural networks with very short bit streams, but you have used 256 bit streams, and also you use LFSR-based bit streams, but we have seen some related work in this area with low discrepancy bit streams.
Yeah, hi to everyone. So yeah, there are some existing works in this domain, but I would say ours is the first where we realized the complete convolution neural network on the hardware. Like there are some work previously done where like part of the logic is running on the processor system and the processor using the same zinc board, while the rest of the portion is usually the demanding complex computation task is done on the FPGA part. But in our work, like we have done implemented the complete stochastic neural network on the FPGA.
But do you think the result will be energy efficient compared to conventional binary? Because with 512 bit stream length, the energy consumption will be really high.
So we don't have an equivalent binary version implemented on the FPGA, which should have been more realistic to make comparisons on with respect to power and also hardware utilization. I also, as I told, there is not much facility on the board to make an exact power estimation. So roughly it's like 96 milliwatts, which I don't say a realistic estimation.
Okay. Thank you, Panano, for the presentation. We can continue with the last presentation, Scaled Population Subtraction for Approximate Computing, presented by Kunal Beharati. Let me prepare the presentation and share my screen.
Scale population subtraction for approximate computing. In this talk, I will go over stochastic computing followed by scale population arithmetic. With that background, we will introduce the basic SP subtraction idea and go over the different designs and look at their error performance. Stochastic computing is a scheme in where the numerator is the number of ones in the bit vector and the denominator is the number of bits in the bit vector. SC allows for arithmetic operations to be realized using simple logic circuits as shown in the figure, where you can realize addition between X and Y using a simple OR gate. The second advantage of using SC is that the number representation is more tolerant to single bit errors. However, SC has a runtime complexity of pi, where pi is the length of the bit vector. In addition, the result of the arithmetic operation's accuracy is dependent on the density and randomness of ones in the binary bit vectors. And third, the range of values that can be represented is limited to just 0 and 1. Scale population arithmetic, or SP, was designed to overcome some of these limitations. So SP arithmetic is designed to avoid the inherent serialization of SC, and all operations in SP are realized using a constant gate delay. In addition, SP uses a number representation that reduces computational errors and allows for a wider range of numbers. SP arithmetic, however, only provides methods for addition and multiplication and not subtraction. The SP number representation relies on two terms, the sigma or exponent term and the pi or the population vector term. Using sigma and pi, it allows us to represent a larger range of numbers larger range of numbers. An example is shown on this slide where we can represent the number 1.5 using a sigma term of 10 and a pi term of 1. Next, let's have a look at the SP subtraction idea. Now, SP arithmetic provides us methods to modify the exponent and pi terms of a given input number to suit our needs. So the way we are going to perform subtraction is to compute a minus b. First, we are going to equalize the exponent terms. Once the exponent terms are equal, we are free to manipulate the pi terms to compute b minus a. We compute b minus a using the equation on this highlighted on this slide. As you can see in the equation, there are only two operations. The first operation is addition, which can be easily achieved using SP adders. Second, anytime we perform a subtraction, it's always a subtraction from 1. Subtracting a number from 1 in the SP number representation is extremely simple and involves just complementing bits of the vector x. A second problem that arises is that SP doesn't natively support negative numbers. So if a is greater than b, we get a result where all the resultant bits are 1, and we call this saturation. We get around this problem by implementing the design shown in the figure on the right. We implement the computation paths for both a and b, and we pick the path that hasn't saturated, and we will also appropriately set the sign bit. Now that we have seen the basic SP subtractor idea, we are going to look at practical implementations of the SP subtractor. We are going to explore two independent axes. The first is going to involve use of different SP adders, and the second axis is going to explore input rescaling. First, let's look at SP subtraction with regular addition. Regular adders are nothing but SC-based adders where we use a bank of OR gates to compute the sum of x and y. We'll use as many OR gates as the length of the population bit vector. The RMSE after our experiments was 0.0723, where we performed 10,000 experiments for different combinations of A and B to compute A minus B. In the three graphs, we plot our results. The graph on the left represents RMSE versus the exact result. The exact result here is the mathematical difference between A minus B. In the graph in the middle, we plot the actual result of our subtraction versus the exact mathematical result. And the graph on the right represents the error percentage versus the exact mathematical results. We have repeated the experiment for different population sizes of 40, 100, and 200. Now we will briefly introduce skewed and skewed star addition and population vector doublers. So skewed addition was a method presented by the SP arithmetic, where instead of using OR gates to AND x and y, we achieve addition by taking the left half of the bit vector x and appending it with the right half of the bit vector y. Performing addition in such a manner reduces errors because it avoids inaccuracies caused by the ones in the bit vectors lining up together. However, a consequence of performing skewed addition is that the resultant vector is half its true value. We compensate for this by increasing the scaling term by a value of 1. Skewed star addition is an improvement over skewed addition to get more accurate results, where to add x and y, we take the bit vector of x and concatenate it with the bit vector y to get the resultant bit vector z, which is going to be twice as long as either of the two inputs. Skewed star addition, just like skewed addition, will result in a value that's half the exact value. Now, if we use skewed addition or skewed star addition for subtraction, we face a problem because we cannot modify the exponent term mid-subtraction. A solution, an alternate solution to doubling the result is to double the number of ones in the population vector of the result population vector. And we double the number of ones using a unit called a population doubler, shown here on the right. The population doubler for any input will output a result that has twice as many ones as the input. And the input-output value relationship of the population doubler is shown here on the bottom right. The maximum value that can be represented by a population doubler is 1. And that is why we see that after an input value of 0.5, ideally the output of the population doubler saturates to a value of 1. When we realize SP subtraction with skewed addition, we got an RMSE of 0.0848, which was greater than that of regular addition. And when we implemented SP subtraction with skewed star addition, we got the best RMSE so far of 0.0579. Now, observe the rightmost graph, which demonstrates the error percentage with respect to the exact result. The exact result is high when the error percentage is high when the exact result is small, and the error percentage is low when the exact result is large. We are going to use this to our advantage in input rescaling. So in input rescaling, we're going to take our skewed star adders, and then we are going to scale the inputs A and B prior to subtraction to try and get larger results, because larger exact differences yield smaller errors. So the implementation is shown here on the right, where we take our basic skewed star subtractor design, right? We take an input A and B, perform the subtraction, and if the result is less than some threshold, then we repeat the subtraction after doubling the values of A and B. We track how many times the numbers A and B have been doubled. At the end of the computation, we will modify the exponent of the result accordingly. So here on this slide, we see the results for SP subtraction with input rescaling. The threshold for rescaling D was experimentally determined to be 0.5. And you can see the average RMSE across all experiments was 0.048. The graph on the bottom right demonstrates the average RMSE across all 4 designs that we have seen so far. And we can see that skewed star addition with input rescaling gives us the lowest RMSE. Next, we realized the skewed star subtractor with input rescaling using Synopsys DC in the 45 nanometer NAND gate technology, and generated the area, power, and delay numbers in order to compare with fixed point binary subtractors. The skewed star design that we realized, we did not realize both paths of computation, but instead realized a single path, and appropriately adjusted the delay where the single path is used twice to compute both A minus B and B minus A. In addition, the units like the doublers doublers or the population vector exponent modifiers were not counted as part of the area, because SP subtraction is going to be part of an SP arithmetic module where all these units are shared across adders, multipliers, subtractors, etc. In this table, you can see that the skewed star subtractors are better in terms of area, delay, and power when compared to the fixed point designs. However, it must be stated that the precision of the fixed point designs is going to be always greater than the corresponding skewed star design. In conclusion, we have presented a method to perform SP subtraction, something that was previously missing in SP arithmetic. We have provided different types of subtractor designs, and you have a choice of choosing a simpler design, but at the cost of computational errors. And lastly, our SP subtractor design has reduced area, delay, and power numbers when compared to a traditional fixed point binary subtractor. And because we are using the SP number representation, we have an improved tolerance to bit errors.
Okay, thank you for the presentation. Any questions for the presenter? Okay, if not, let me ask a quick question. What are the source of errors in the subtraction designs? And how does population vector length affect the subtraction results?
Well, in our design, especially in the skewed star design that we presented at the end, the best subtractor, the only source of errors is that population doubler that we described. So everything else, so if you can like realize an ideal population doubler, then your subtraction results are going to be perfect. So that's sort of what we're working on next. We're trying to improve how well the population doubler does, because the more ideal the population doubler, the more realist, the more close, the more accurate the results are going to be.
Mm-hmm. Got it. Thank you for the presentation. We have a few minutes to the next session on test and verification. I pass the session to the next one. So thank you, everyone.
Thank you.